Since this is a statistics class, we should start off with the meaning of statistics. Statistics is the science of collecting, describing, and interpreting data. Before we talk about what it means to collect, describe, and interpret data, we should talk about the meaning of the word data. The word data is actually plural for another word, which is data value. A data value is a piece of information that describes something about a person, animal, thing, or place. Let's say that a person is 57 inches tall. If a person is 57 inches tall, then 57 inches is a data value that describes something about this person. It describes the person's height. If a house is 250 square feet, then 250 square feet is a data value that describes something about the house. It's a data value that describes something about this specific house right here. Let's also say that a car is worth $200,000. I'll try to draw a car. It's not a very good job. I'll try to put a window here so that it looks kind of like a car. If this car is worth $200,000, then $200,000 is a data value that describes something about this car. So far we have three data values on the board. 57 inches is the data value, 250 square feet is the data value, and $200,000 is the data value. Each of these three things that we see here is a piece of information that describes something about a person, a place, or a thing. We can also do an example with an animal. What if we have a dog, and that dog is 30 pounds? What if the dog weighs 30 pounds? Well then, 30 pounds is a data value that describes something about the dog. I'm probably going to embarrass myself trying to draw a picture of a dog. Maybe I'll just write the word dog right here. And we'll imagine that this is a dog right here. So each of these is a data value. We have the first data value, the second data value, the third data value, and the fourth data value. And a data value doesn't have to be a number. It could be a word. So what if we have a piece of paper, and the piece of paper is green? Well then, the word green is a data value that describes something about this piece of paper. So a data value doesn't have to be a number. It just has to be a piece of information that describes something about a person, animal, thing, or place. Each of these 5 pieces of information is a data value. And I said that the word green is a data value, even though it's not a number. All 5 pieces of information together would be called data. So we could say that inside this circle we have data because we have more than one data value. We have a collection of data values. So the word data is just a plural word for data value. When you see the word data, just think of more than one data value. So I'll label this circle with the word data just to show you that inside the circle we have data because we have more than one data value inside of there. And what does it mean to collect data? Collecting data just means seeking out and recording data. If I ask this person, how old are you, or how tall are you, and then I write down the person's answer, then I'm collecting data from this person. If I put this dog on a scale, and then I record the dog's weight on a piece of paper, I'm collecting data from the dog. If I find out the price of this car, and then I record the price of the car, then I'm collecting data about this car. And how do you collect data? Well, collecting data means seeking out and recording data, and the way that you do that depends on the situation. If I want to know a person's height, I can just ask the person, how tall are you? Or I could actually measure the person. If I want to know the height of a tree, then in that case I would have to actually measure the tree. If I wanted to know the color of a piece of paper, I could just look at the piece of paper and I would know what color it is. If I wanted to know the weight of a dog, I could put the dog on a scale, or I could ask the dog's owner how much the dog weighs. I said that a data value is a single piece of information, and data is a collection of information. A data set is a completed set of data. So if my goal is to ask 10 people for their heights, then once I'm finished, the 10 heights that I've recorded would be called a data set because those 10 heights that I've recorded make up all of the data that I meant to record. It's a complete set of data. I said that a data value is a single piece of information, and data is a collection of information. A completed collection of data is called a data set. So if my goal is to record the heights of 10 people, once I'm finished recording those 10 heights, then those 10 heights would be called my data set, because those 10 heights would be the complete collection of data that I meant to record during my data collection project. Once you've collected the data set, the next step is to describe the data set. And what does it mean to describe a data set? When you see the words describing data, you might think of talking about the data, but describing data doesn't actually mean talking about the data. It means presenting the data. It actually means presenting the data in a way that's summarized and easier to understand. It means presenting a boiled down version of the data. It's easier for you to make sense out of, and it's easier for other people to make sense out of. Let's look at an example of describing a set of data. Let's say that I wanted to collect data from 10 college students who were taking classes during the day, and from 10 college students who were taking classes at night. So these are the students that I'm collecting data from. And also imagine that I'm asking each of these students how many hours they're working per week. And imagine that these are their answers. So I've asked 10 college students who take classes during the day how many hours they're working per week, and I got these 10 answers. And I asked these 10 students who are taking classes at night how many hours they're working per week, and I got these 10 answers. Now, by just looking at these numbers, I can get a little bit of a sense of what the data seems to be showing. It looks like the 10 students who are working, it looks like the 10 students who are taking classes during the day are working fewer hours per week. And it looks like the 10 students who are taking classes at night are working more hours per week, because over here, most of the numbers are in the 20s. Well, actually, all of the numbers are in the 10s or 20s. And over here, all the numbers are in most of the numbers are in the 30s and 40s, and we have 120 right here. But if I wanted to present this data to someone so that they could easily understand what this data is showing, I wouldn't want to just give them the 20 numbers. I would want to give them a summarized version of the data set. How can I summarize this data set so that it's easier to understand, and so that it won't take as much effort for someone to understand what my data is showing? One thing I could do is calculate the average of these 10 students, and also calculate the average of these 10 students. Then the person who is looking at my data can just look at the average of this group of people and look at the average of this group of people and look at the difference between the two averages. So let's actually see what the averages come out to. I can get my calculator. To get the average of these 10 students, I have to add the numbers and divide the total by 10, since there's 10 people. So when I add and divide by 10 to get the average, it comes out to 17.6. And I can do the same thing over here. I can get the average of those 10 students. I just add the 10 numbers and divide the total by 10. Over here, it comes out to 36.5. So if I show these two averages to someone so that they can see that this average is lower and this average is higher, I've described my data set to a person because I've given them a summarized version of the data set that allows them to see what my data set is showing. Now, what's another option to describe this data set besides just calculating these two averages? What's another way to present the data set to someone? Well, I could also show a graph like this. I could create a bar graph. Maybe it goes up by 5, 10, 15, and 20. So then this bar would go up to 17.6, which is right here, or about right there. And this other bar for the night students would go up higher. So now, what this graph is doing is describing my data set. This graph is describing what message my data is showing. This graph is showing that the 10 night students are working more hours than the 10 day students. And if I look at this graph, then this graph is describing my data set to me. And if I show this graph to someone else, then this graph is describing my data set to that other person. So whenever you summarize your data set and present it in a summarized form, such as by calculating averages, like we did here, or by showing a graph, you're describing your data set. That's the process of describing data. The process of describing data is summarizing the data and then presenting it in a summarized form. Now, what does interpreting data mean? Interpreting data is when you actually make a conclusion about what the data set is showing to be true. When you make a conclusion about what the data set is showing about the world that we live in, you're interpreting the data set. And when you interpret the data set in a data collection project, you're typically trying to make a conclusion that extends beyond the participants that are in your study. For example, once I collect data from these 10 day students and collect data from these 10 night students, I'm not going to want to just make a conclusion about these 10 students here and these 10 students over here. I'm going to want to make a conclusion about day students in general and night students in general. Let's say that there's about, well, I'm just going to make up some numbers. Maybe there's about 12 million day students in the US and 7 million night students in the US. The goal of my data collection project might be to actually make a conclusion about whether the 12 million day students are working fewer hours and whether the 7 million night students are working more hours. So I could be actually trying to make a conclusion about a big category of people here and a big category of people over here based on the participants that I've selected. And if I actually make a conclusion that all of the day students in the US are working fewer hours on average, and all of the night students in the US over here are working more hours on average, I've interpreted my data set once I come to that conclusion. I've interpreted my data set because I've taken the data that I've collected from these people and I've reached a conclusion about a bigger category of people that goes beyond just the people that I've selected to collect data from. And since people who collect data try to make conclusions, or since they do make conclusions that go beyond the specific people that they've selected to collect data from, the conclusions that they make actually aren't proven conclusions. Meaning, if you interpret your data and you make a conclusion about a big category of people based on a small group of volunteers, then there's always a chance that you'll make a wrong conclusion. But the good news is, when data collection is done properly, and when the data is interpreted properly, meaning when people make the conclusions properly, then most of the time correct conclusions will be made, and incorrect conclusions will be made less often. But whenever you make a conclusion about a bigger category of people, then whenever you make a conclusion that goes beyond your volunteers and is about a big category of people, there's always a risk of making a wrong conclusion. So nothing is proven. Let's talk about the difference between a data value and an observational unit. And then afterward, we'll also talk about another word called a variable. First, I'll put a new slide right here. So we already talked about how a data value is a piece of information that describes a person, animal, thing, or place. And we said that each of these 5 pieces of information was a different data value. Each person, animal, thing, or place that provides a data value is called an observational unit. So if I recorded this data value from this person, for example, if this person told me that he or she is 57 inches tall, then the person is an observational unit. If I found out that this house is 250 square feet, then 250 square feet is the data value, and the house itself is an observational unit. So basically, a data value describes something about an observational unit. And an observational unit is just a person, animal, thing, or place. An observational unit is just a person, animal, thing, or place that's being measured or studied in some way. If I found out that this car is worth $200,000, then $200,000 is the data value, and the car is the observational unit. If I weighed this dog, and it turned out that the dog was 30 pounds, then 30 pounds is the data value, and the dog is the observational unit. And if I looked at this piece of paper and I recorded that the paper is green, then green is the data value, and the piece of paper is the observational unit. So the observational units are just the people, animals, things, or places that are being studied or being measured. The researcher is the person who's collecting the data. So if I ask this person, how tall are you? And the person tells me that he or she is 57 inches tall, then I'm the researcher because I'm collecting the data. The person is the observational unit because the person is what I'm collecting data about. I'm collecting data about the person, so the person is the observational unit, and 57 inches is the data value because that's the piece of information that describes the person. If I record the square feet of a house, then I'm the researcher because I'm collecting the data. The house is the observational unit because the house is what's being measured, or the house is what I'm collecting information about, and 250 square feet is the data value. So if I collect all of these data values, if I collect the height of the person, the square feet of the house, the price of the car, the weight of the dog, and the color of the piece of paper, then I'm the researcher in all of the examples because I'm the person who's collecting the data. But in each example, the observational unit is different because here I'm collecting information about the person, here I'm collecting information about the house. So we've covered the difference between a data value, an observational unit, and a researcher. Now let's talk about the word participants. A participant is basically a human observational unit. So if I'm collecting data from people instead of things or places, then the people who are providing me with the data would be called my participants. even though they could also be called observational units. For example, if I had a group of people taking a survey, I would probably call those people participants and not observational units. So a participant is really a specific type of observational unit. The reason why people are called participants is because they're actually participating in your study when they provide you with data. They're actually helping you by actually actively participating in your study. Unlike a house, which wouldn't actually be participating. If I'm recording the square feet of different houses, the houses aren't actually participating, they're just being measured, which is why, or you could say that they're being observed, which is why you would just call them observational units. Let's now look at an example of a larger and more realistic looking data set. You just have to pretend that this data set was recorded from 5 college students. In this data set, commute distance means the number of miles that each person commutes to school each day. These 5 people over here are the 5 participants. You could also call them observational units, but participants would be the more specific term. A participant is a human observational unit. This is what a data set usually looks like. Usually the data is entered into a computer spreadsheet with rows and columns. In a spreadsheet, each row contains data from one person, animal, thing, or place. In other words, each row contains data from one observational unit. If the data was collected from people, you would more specifically say that each row contains data from one participant. In this spreadsheet, you can see that person 1 has brown hair, that person 1 is a psychology major, that person 1 is a freshman, and that person 1 has 4 siblings. You can see that person 2 has red hair, that person 2 is a business major, that person 2 is a sophomore, and that person 2 has 3 siblings. In a spreadsheet, each cell or box contains one data value. For example, right here, freshman would be a data value, and right here, 12 would be a data value. The title of each column is called a variable. A variable is something that can differ between different people, animals, things, places, or points in time. A variable is just something that isn't always the same. The word variable means able to vary, so anything that's able to vary is a variable. In this example, hair color is a variable because different people have different hair colors. College major is a variable because different people have different college majors. Grade level is a variable because different people have different grade levels. Number of siblings is a variable because different people have different numbers of siblings. Shoe size, account balance, height, and commute distance are also variables because not everyone has the same shoe size, not everyone has the same account balance, not everyone has the same height, and not everyone has the same commute distance. I said that the title of a column of data in a spreadsheet is considered a variable. However, the title of a column is only considered a variable if it's possible to get different data values inside that column of data. The reason why number of siblings is considered a variable is because different people have different numbers of siblings. What if I was asking these 5 people, how many birthdays do you have per year? And one of the columns in my spreadsheet had a title that said number of birthdays per year. Number of birthdays per year actually wouldn't be a variable. It would be a column in my spreadsheet, but it wouldn't be a variable. The reason why is because number of birthdays per year isn't something that varies across different people. Every person in the world only has one birthday per year. That means that no matter how many people I asked that question to, every person would tell me one. That means that number of birthdays per year actually isn't a variable. A variable is something that is able to vary. Something that isn't able to vary isn't a variable. That's why number of birthdays per year wouldn't be a variable. You might be wondering, if all 5 people told me that they have 4 siblings, would that mean that number of siblings isn't a variable? Number of siblings would still be a variable because even if all 5 people told me the same answer, it would still be possible to get a person with a different answer. If I ask a 6th person, how many siblings do you have, I might get a different answer, even if all 5 previous people told me the same answer. In other words, even if all 5 people told me that they have the same number of siblings is still something that's able to vary. That's why number of siblings would still be considered a variable. Overall, in a spreadsheet, each person has data in a certain row. Each column title is a variable, and each box contains one data value. So basically you have rows for people or participants, you have columns for variables, and you have boxes or cells for data values. You can actually find the number of data values by multiplying the number of people by the number of variables. Here I have 5 people, and I have 1, 2, 3, 4, 5, 6, 7, 8 variables. So 5 times 8 means there are 40 data values inside the spreadsheet right here. I'm going to show you 3 other examples of spreadsheet data sets. In this example, I'm recording the color, miles per gallon, and model of 3 different cars. In this example, the 3 cars are the observational units, because they're the 3 things that are being observed. Color, miles per gallon, and model are the 3 variables, because those are the 3 things that are different between the different cars. The cars have different colors, they have different miles per gallon, and they have different models. These 9 values in here are the 9 data values in the spreadsheet. In this example down here, I'm recording the price, square feet, and number of floors of 3 different houses. In this example, the 3 houses are the observational units, because they're the 3 things that are being observed or studied. Price, square feet, and number of floors are the 3 variables, because those are the 3 things that are different between these different houses. These 9 values in here are the 9 data values that have been recorded. In this last example down here, I'm recording the height, income, and level of education of 3 different people. In this example, the 3 people are the observational units, because in this case, these 3 people are being observed or studied. But in this example, you could also call them participants, because they're participating in the study by volunteering. So remember that a participant is a human observational unit. A participant is a certain type of observational unit. And in this example, height, income, and level of education are the variables, because those are the 3 things that are different between the different people. And these 9 values in here are the 9 data values that have been recorded. Let's talk about 2 different types of variables. A quantitative variable is a variable in which each data value stands for the number of something or the amount of something. Let's look at number of siblings, shoe size, account balance, height, and commute distance. Let's look at those 5 variables. We can see that in these 5 columns of data right here, each data value stands for the number of something or the amount of something. Since that is true, we can say that these 5 variables up here are all quantitative variables. A qualitative variable is a variable in which each data value shows that a person, animal, thing, or place is a member of a certain category. Let's look at hair color, college major, and grade level. We can see that in these 3 columns of data, each data value doesn't stand for the number of something or the amount of something. In these 3 columns of data, each data value shows that a person is a member of a certain category. For example, this data value right here shows that this person is a member of the category of people who have brown hair. This data value right here is showing that this person is a member of the category of people who are college sophomores. This data value right here is showing that this person is a member of the category of people who are psychology majors. Since we can see that all of the data values in these 3 columns show category membership, we can say that these 3 columns of data, we can say that these 3 variables are qualitative variables. Hair color, college major, and grade level would all be qualitative variables. Just because a column of data has numbers inside of it doesn't necessarily mean that the variable is quantitative. Imagine that I was asking these 5 people to tell me their student ID numbers, and I had a column of data over here that was titled Student ID Number. Student ID number actually wouldn't be a quantitative variable because a student ID number doesn't stand for a number of something or an amount of something. A student ID number is just a label for the student. A student ID number is basically another name for the student. So if I had a column of student ID numbers over here, the numbers in that column wouldn't stand for amounts. They would just be labels or names for the different students. That's why the student ID number variable wouldn't be a quantitative variable. Even though my student ID number column would have numbers inside of it, student ID number wouldn't be a quantitative variable. In order for a variable to be quantitative, the data inside of that column has to stand for amounts or numbers of things. Some types of numbers actually don't stand for the number of something or the amount of something. Student ID numbers are one example. Other examples could include social security numbers, jersey numbers, or driver's license numbers. Social security number, driver's license number, and jersey number wouldn't be quantitative variables because a person's social security number, driver's license number, or jersey number doesn't stand for the number of something or the amount of something. Social security number, driver's license number, and jersey number would actually be qualitative variables. If you think about it, a person's social security number shows that the person is a member of a certain category. The category is a category of one person. Also, a person's jersey number shows that a person is a member of a certain category. It just happens to be that that category only includes one person. Same thing is true about driver's license numbers. So, variables like driver's license numbers, jersey numbers, and social security numbers are qualitative variables because the data values are only labels for people, animals, or things. The data values don't stand for the number of something or the amount of something. Let's talk about two different types of quantitative variables. A quantitative variable can be either a discrete variable or a continuous variable. A discrete variable is a quantitative variable that has gaps between the possible data values, in which no data values can be found. Number of siblings would be a discrete variable because even though data values such as 1, 2, 3, 4, and 5 would be possible, it wouldn't be possible to have a data value between 1 and 2, a data value between 2 and 3, a data value between 3 and 4, or a data value between 4 and 5. For example, a person couldn't have 2.2 children or 4.1 children. Shoe size would also be a discrete variable because even though data values such as 10, 10.5, 11, and 11.5 are possible, it wouldn't be possible to have a data value between 10 and 10.5, between 10.5 and 11, or between 11 and 11.5. For example, a person couldn't have a shoe size of 10.75 or 11.25. Account balance would also be a discrete variable because even though account balances such as $3,000, $3,000.01, or $3,000.02 would be possible, no account balances between those account balances would be possible. For example, a person couldn't have an account balance of $3,000 and 0.017 cents. A continuous variable is a quantitative variable that has no gaps between the possible data values. In other words, a continuous variable is a quantitative variable that has a continuous or solid stream of possible data values. Variables such as height and weight are continuous. Discrete variable is usually something that's counted. Whenever a person counts something, there are gaps between the possible numbers that the person might end up counting. For example, if I count the number of siblings a person has, I might end up counting that the person has one sibling, I might end up counting that the person has two siblings, and I might end up counting that the person has three siblings, but I won't end up counting anything between those numbers. For example, I wouldn't end up counting that a person has 1.2 siblings or 2.3 siblings. So there are gaps between the possible numbers of siblings that might be counted, which is why number of siblings is a discrete variable. If I count the number of bathrooms that a person has in his or her house, I might end up counting that the person has one bathroom. I might end up counting that the person has 1.5 bathrooms if the person has a half bathroom in his or her house. I might end up counting that the person has two bathrooms, but I won't end up counting anything between those numbers. For example, I wouldn't end up counting that a person has 1.2 bathrooms or 1.7 bathrooms. So there are gaps between the possible numbers of bathrooms that might be counted in a house, which is why number of bathrooms would also be a discrete variable. If I count the amount of money that a person has in his or her bank account, I might end up counting $2,000, I might end up counting $2,000.01, or I might end up counting $2,000.02. But I won't end up counting anything between those numbers. For example, I won't end up counting $2,000 and 1.5 cents, or $2,000 and 1.25 cents. So there are gaps between the possible amounts of money that a person might count, which is why account balance would also be a discrete variable. A continuous variable is usually something that's measured, and when something is measured, there are no gaps between the possible values that might be measured. There might be a lower limit on what the amount could be, and an upper limit on what the amount could be, but anything between the lower and upper limit is a possible value that might end up being measured. For example, if I measure a person's height, there might be a lower limit and an upper limit on how tall the person could be, but anything between the lower limit and upper limit is a possible number that I might end up measuring as the person's height. For example, I might end up measuring that the person is 60 inches tall, 61 inches tall, or 62 inches tall, but I might also end up measuring any possible number between those numbers. For example, I might end up measuring that the person is 60.17 inches tall, or I might end up measuring that the person is 61.297 inches tall. So when a variable is continuous, there's a lower limit and an upper limit on what the amount could be, but anything between the lower and upper limit is a possible value that might be measured. When you measure a person's height with one of those sliding scales, notice how the scale moves smoothly from one end of the scale to the next. It moves smoothly across all of the possible heights that the person might have. The reason why is because any possible point on that number line is a possible height that the person might have. If height was a discrete variable, and there were gaps between the possible heights, then that scale would jump from one possible height to the next possible height. It wouldn't move smoothly across the number line. So another example of a continuous variable could be temperature. There might be a lower limit on how cold it could be, and an upper limit on how hot it could be, but anything between those two temperatures would be a possible temperature that you might find on a certain day. For example, on a certain day it might be 80.377 degrees, or it might be 80.9775 degrees. And another example of a continuous variable could be weight. A person could be 160 pounds, 161 pounds, or 162 pounds, but anything between those possible numbers is also a possible weight that a person could have. For example, a person could be 160.17 pounds or 161.133 pounds. So there are no gaps between the possible weights that a person might have, which is why weight is also a continuous variable. So overall, a discrete variable is usually something that's counted. And when something is counted, there are gaps between the possible numbers that might end up being counted. A continuous variable is usually something that's measured, like height, weight, or temperature. And when something is measured, there are no gaps between the possible numbers that might end up being measured. A discrete variable could also be something that's only created in certain amounts. For example, when they created shoe sizes, they decided that shoe sizes would be 10, 10.5, 11, 11.5, and so on, but nothing in between. They decided that there wouldn't be a shoe size of 10.2 or 10.3. So when something is only created in certain amounts, then there are gaps between the possible amounts that might be found, and the variable becomes a discrete variable. Let's look at some examples of some quantitative variables, and let's think about whether each variable is discrete or continuous. Remember, a quantitative variable can be either discrete or continuous. Let's start with number of siblings. Then number of TVs owned. The number of TVs that people own. Maybe account balance, the amount of money people have in the bank. Or maybe we could do shoe size first and then account balance. Then maybe commute distance, the distance that a person has to travel to get to work or to school. Then maybe temperature, height, and maybe amount of time spent on homework per week. Now it's a discrete quantitative variable if there's gaps in which you can't have any possible values. And it's a continuous quantitative variable if there are no gaps, and a value can be anywhere on the number line. And let's think about this for every example. Let's start with number of siblings. A person can have 0 siblings. A person can have 1 sibling. A person can have 2 siblings or 3 siblings. So the number of siblings a person has can be a whole number, but it can't be anywhere in here. For example, a person can't have 0.5 or 0.6 siblings, and a person's number of siblings also can't be in here. It can't be 1.1 or 1.2. So we can already see that we have 2 gaps in the number line, which we can't have any possible values. So the areas that I'm marking in red are where there can never be any values. But we can have values here. A person can have 0 siblings. A person can have 1 sibling or 2 or 3 siblings. So I'm going to mark off the areas where we can have values in green. So wherever we have a green place on the number line is where we have a place where a person's value can fall on the number line. And we can see that number of siblings is discrete because we do have these red areas that are gaps in the number line in which there will never be any values. There will never be any values in any of these red areas. Number of TVs works the same way. I could just copy and paste this for number of TVs. A person can have 0, 1, 2, or 3, or 4 TVs. So a person can have a value here. A person can have 0 TVs. A person can have a value here because a person can have 1 TV. A person's data value can fall at any of these green areas. The number of TVs a person owns could be 0, 1, 2, 3, 4, or even 5 or 6. But it can't be anywhere in between 0 and 1, or between 1 and 2. It can't be between 2 whole numbers. So number of TVs is also discrete because we have these red gap areas where a person will never fall on the number line. What about shoe size? Well, shoe size can be, a person's shoe size might be 10. It could even be lower than 10, but let's just start at 10. It could be 10.5. It could be 11, or 11.5, or 12. So it can be either a whole number or a number with a 0.5 at the end. But it can never be anything in between any of these numbers. I've never heard of a person who could have a shoe size of 10.7 or 10.8. So you can't have any values in here. Like I said, a shoe size can't be 10.7, 10.8, or 10.9. You also can't have a shoe size in between here. For example, it can't be 10.2 or 10.3. So this is also a red gap area. And let's mark off the possible values. One way to think about this is, if it's possible to mark off the possible values, and the possible values are always separated like this with red gaps in between, then it's discrete. What about account balance? We could maybe start at let's start at 0. That's the lowest a person's account balance could be unless they have a negative account balance. Then after that, let's go up to 0.01, which is 1 cent. That's the next highest number that a person's account balance could be. A person's account balance could be 2 cents or 3 cents. And the possible values would just keep going up. It would be 0.4, 0.5, 0.6, and so on. So these are the possible values that a person could have for their account balance. And it's not possible to have anything in between. For example, a person's account balance couldn't be right here at 0.013 or a person's account balance couldn't be right here at 0.007 or 0.008. And a person's account balance couldn't be right here at 0.013 or 0.014. And the numbers in between 2 cents and 3 cents would be numbers like 0.024 or 0.025. Those also aren't possible. So we can't have anything in any of these areas. So it is a discrete variable. We have these possible values that are separated from each other, and between each of these pairs of possible values, there's this red gap area in between. There's a red gap area between 1 cent and 2 cents. There's a red gap area between 2 cents and 3 cents. And we would keep having more of these gap areas if we kept going up higher. So actually anything that has to do with dollar amounts is usually discrete, because you can't have anything between these values. You can't have anything between these two values here or between these two values here. Each of the first 4 examples were all discrete variables. Number of siblings, number of TVs owned, shoe size, and account balance were all discrete variables. They were discrete variables because there were gaps between the possible values on the number line. In other words, the possible values were separated from each other. They were separated by these red gap areas. Commute distance, temperature, height, and amount of time spent on homework per week would actually all be continuous variables. They are continuous variables because in each of these 4 examples, in commute distance, temperature, height, and amount of time spent on homework per week, the possible values aren't separated from each other. We don't have any of these gap areas. So for each of these last 4 examples, the number line would be like this. We might have a lowest possible value, and there might be a highest possible value, meaning there might be a limit on how low a value can be or on how high a value can be. But anything between the lowest and highest values is a possible value, meaning there's no interruptions or gaps in the number line in between the lowest and highest values. So up here, I marked off every part of the number line that was a possible value in green. The reason why this was green is because a value can fall here on the number line, and the reason why this was green is because a value can fall here. In each of these last four examples, which are the continuous variables, everything between the lowest possible value and the highest possible value is green, because really a value can fall anywhere on the number line in each of these last four examples. So this is what the number line looks like for each of these four continuous variables. Because in each of these four examples, a person's value can be anywhere between the lowest possible value and the highest possible value. There are no restrictions on where a value can be in between the lowest value and the highest value. That's why this number line doesn't have any of those red gap areas where a value can't fall. So what the word discrete means is separated or broken up. So we can see that these four variables are discrete because the possible values are separated from each other. They're separated by these gaps in which no values can ever fall. But what continuous means is no interruptions or no breaks. So in each of these last four examples, the number line continues without any interruptions or gaps. When a variable is discrete, the number line is like a set of stepping stones. And when a variable is continuous, the number line is like a sidewalk that continues without any gaps. In other words, in each of these four continuous variables, a value can be anywhere between the lowest and highest values. So you could remember that if a variable is continuous, then the number line continues without any gaps. I also wanted to talk about what makes a variable discrete instead of continuous. Often the reason why a variable becomes a discrete variable is because some things are only created in certain amounts. For example, people only come in whole numbers. TVs are only made in whole numbers. No one would make 2.5 TVs. Also, shoe sizes are only created in certain amounts. People who make shoes have decided that the possible shoe sizes should be 10, 10.5, and 11, and so on. And they've decided that there shouldn't be any shoe sizes in between these numbers. But a lot of things that happen in nature, or a lot of naturally occurring amounts, don't have these rules on what values are possible. Things like temperature, height, time, or even things like amount of rainfall can take on any value. There might be a lowest possible value and a highest possible value, but the value can take on any number in between those lowest and highest possible values. Let's talk about two different types of qualitative variables. Remember that a qualitative variable is a variable in which each data value shows that a person, animal, thing, or place is a member of a certain category. A qualitative variable can be a nominal variable or an ordinal variable. Let's talk about ordinal first. An ordinal variable is a qualitative variable in which the possible categories follow an order from lowest to highest. Grade level is an ordinal variable because the possible categories of freshman, sophomore, junior, and senior follow in order from lowest to highest. The opposite of an ordinal variable is a nominal variable. A nominal variable is a qualitative variable in which the possible categories don't follow in order from lowest to highest. College major would be a nominal variable because the possible college majors that we might record don't follow in order from lowest to highest. All possible categories are equal. Hair color would also be a nominal variable because the possible hair colors that we might record don't follow in order from lowest to highest. All categories are considered to be at the same level. I wanted to go through some examples of some ordinal variables, and I wanted to make a few points while I'm going through them. When you see an example like grade level, you might think that an ordinal variable has to be something where a person starts at the first category and then moves up one category at a time because, well, a person has to be a freshman before they can become a sophomore, and a person has to be a sophomore before they can become a junior. But even though that's true in this example, not every ordinal variable is like that. Not every ordinal variable is a series of categories where a person has to move up one category at a time. For example, a person could win a gold medal without ever having won a silver or a bronze first. A person could jump straight to winning a gold medal, or a person could win a silver medal without ever having won a bronze medal first. So a person could start here, or a person could start here. They don't have to start at the lowest category and then move up one category at a time. What's another example? These are donation categories. Sometimes when people are donating, they'll put people into categories where the people who donated the lowest amount will be in one group, and people who donated more will be in a higher group, and people who donated even more will be in an even higher group. So maybe a library will say that anyone who donated less than $100 is a patron. Anyone who donated between 1 and 200 is a friend of the library, and anyone who donated more than 200 is a supporter of the library. A person, in this case, wouldn't have to be a patron first. I mean, a person wouldn't have to start as a patron and then move up to a friend and then move up to a supporter. A person could donate $250 and become a friend right away, or a person could donate $400 and become a supporter right away. Just like how, in my other example, a person doesn't have to win a bronze first and then win a silver and then win a gold. A person could win a silver medal first or win a gold medal first. So it's not necessarily a series of categories where a person has to start at the bottom and then move up one category at a time. Also, sometimes or often an ordinal variable is based on a quantitative variable. And I'll give you an example of what I mean. You can take a quantitative variable and actually change it into an ordinal variable. So the variable of age in years is a quantitative variable because you have numbers like 16, 17, or 18 years old. But if instead of thinking about age in years, I think about age as being age categories, then in that case, age turns into the ordinal variable of age group. So even though age in years is quantitative, age group with these types of categories is ordinal. And the variable of age becomes ordinal once I create these categories, like these categories we have here. If I'm doing a survey and I'm asking people how old are you in years, then age is a quantitative variable in my survey. If I'm doing a survey and I'm asking people, are you a child, adolescent, or an adult, then age is an ordinal variable in my survey. So if I'm doing a survey, I can actually decide whether I want age to be a quantitative variable or an ordinal variable in my survey. If you think about earthquake severity, or how severe an earthquake is, as being a number on the Richter scale, then it's a quantitative variable. But if instead of thinking about it as a number, you think about earthquake categories like mild, moderate, or severe, then earthquake severity isn't quantitative anymore because it's no longer has numbers. It now has categories, so it becomes an ordinal variable. Also, if a variable is ordinal, it doesn't mean that higher categories are necessarily better than lower categories. For example, you might say that it's better to win a gold medal than to win a silver medal, but a severe earthquake isn't better than a moderate earthquake. So sometimes with some examples, higher categories are actually worse than lower categories. And in some examples, higher categories aren't really better or worse than lower categories. For example, when you think about child, adolescent, and adult, none of these categories are really better than other categories. None of these three categories are really better than any other categories. It's not better to be an adult than to be an adolescent. It's not better to be a child than to be an adolescent. So I think that covers the points that I wanted to make about ordinal variables. Let's think about some examples of nominal variables. Remember that a qualitative or categorical variable can be nominal or ordinal. It's ordinal if the possible categories follow an order from lowest to highest, and it's a nominal variable if there is no order to the possible categories and all categories are equal. So if a variable is nominal, that really just means that there is no order to the possible categories. So it's the lack of an order that makes it a nominal variable. A lot of demographic variables are nominal, like gender and ethnicity. Also, hair color is nominal because if you think about the categories like brown, blonde, and so on, there's no order to the possible categories. For example, it's hard to really say whether blonde should go first or whether brown should go first because there's no real official order to these hair colors. It's not like grade level where the official order is freshman, sophomore, junior, senior. What about something like, college major? Like, you think about the possible college majors like psychology, sociology, business, engineering, those possible college majors don't have an order from lowest to highest. They're all pretty much considered equal. It's not like grade level, where a senior is above a junior and a junior is above a sophomore. So since there's no official order from lowest to highest, college major is a nominal variable. If I wrote out all of the possible college majors right here, then there would be no clear way for me to order them from lowest to highest. So it's not an ordinal variable, it's a nominal variable because the possible categories don't have an order from lowest to highest. Food preferences, like people who like, you might have people who like sweet food, people who like spicy food, people who like other types of food such as sour or bitter food, I guess. Those possible categories don't have an order from lowest to highest. All of the possible food preference categories are pretty much equal to each other. For example, people who like spicy food aren't above people who like sweet food. No category is above any other category. Types of athletes. You have soccer players, football players, basketball players, and other types of athletes. No type of athlete would really be considered above another type of athlete. So if I wrote out all of the possible types of athletes here, I couldn't really order the categories from lowest to highest because they don't follow an official order from lowest to highest. They're all pretty much equal to each other, so type of athlete would also be a nominal variable. So it's when the possible categories don't follow an official order from lowest to highest, and all the categories are equal. That's when a qualitative variable is a nominal variable. When the possible categories do follow an order from lowest to highest, like child, adolescent, adult, or freshman, sophomore, junior, senior, that's when the qualitative variable is an ordinal variable. So these are the types of variables that we have covered. Quantitative variables involve numbers or amounts of things, and qualitative variables involve categories or types of things. The two types of quantitative variables are discrete and continuous variables. Discrete variables have gaps between the possible values, and continuous variables have no gaps between the possible values. The two types of qualitative variables were nominal variables and ordinal variables. Nominal variables have no order to the possible categories, and ordinal variables do have an order to the possible categories. It's important to remember that only a qualitative variable can be ordinal. A quantitative variable can't be ordinal. Sometimes a person will think that since the possible ages that a person could have in years, such as 13, 14, and 15, follow an order from lowest to highest, that age in years must be an ordinal variable. But those ages in years do follow an order from lowest to highest, but those ages aren't categories. They're specific amounts of things. So, since age in years is quantitative, it won't be an ordinal variable. It'll be one of these two variables. One last point I wanted to make is that only a qualitative variable can be ordinal. A quantitative variable can't be ordinal. Sometimes a person will think that since the possible ages in years that a person might have, such as 31, 32, and 33, follow an order from lowest to highest, that age in years must be an ordinal variable. But those numbers, like 31, 32, and 33, are specific amounts of age. They're not categories of age, which means that age in years is a quantitative variable. In order for a variable to be ordinal, it has to involve ordered categories. not ordered amounts.